gives us a pretty exciting set of things. We're going to start off with looking at some of the latest developments on CHERI, which Franz Fuchs from the University of Cambridge is going to tell us about. Over to you, Franz.
Thank you so much, Jeremy. Compartmentalisation is a mandatory feature in modern security systems. Today, we'll look at CHERI compartmentalisation and see it running on a full-scale operating system. This is not only, obviously, my work. The CHERI effort is a huge team effort, and I'm hugely indebted to the entire CHERI team as well as our collaborators around the globe. So CHERI stands for Capability Hardware Enhanced RISC Instructions. At the core of CHERI are capabilities. A capability authorizes access to a memory. On the right-hand side of the slide, you can see a 128-bit capability. So it is a pointer, so it has a virtual address, but also it is extended for metadata, so it has permissions and bounds. Due to time limits, I'm not going to be able to talk much about CHERI capabilities, and please do ask afterwards or read any of our publications, and there's quite a few CHERI posters around today as well. So compartmentalisation is the separation of privileges. That means if you have a security breach in one of the compartments, it gets contained there and it will not spread out to the entire system. In this demonstration, we'll look at library-based compartmentalisation. So we're looking at user libraries. So this is a linkage-based access mechanism. What it does is that it ensures stack integrity and confidentiality. So libraries or dynamic shared objects are the unit of isolation in library-based compartmentalisation. On the right-hand side, you can see a small diagram showcasing what library compartmentalisation does at its core. On the left-hand side of the diagram, you see the conventional world. You have two libraries, the orange library and the blue library, and they both have one function, function B and function A, and they're on the stack. In the conventional system, we have then one big stack which holds all the stack frames from all the libraries. So if one of the two actors is malicious, they can actually change the stack frame of the other function and of the other library. In the library compartmentalisation world, we have a stack for each library. So now we have a stack for the blue library, and we have a stack for the orange library. And they cannot interfere with each other. I've also drawn other functions there just to make sure that a library can obviously have more than one function. So the library-based compartmentalisation approach is a proven approach. It is currently adopted for RISC-V CHERI standardization. So in the standardization process of CHERI coming into RISC-V, it is already in there, as we believe that compartmentalisation is a core feature of CHERI. Library-based compartmentalisation has been hugely proved on the ARM Morello prototype. So, and we currently see a huge porting effort to CHERI RISC-V, and it's all going very well. So let's look into the running system. So this is a CheriBSD system. It's running on a DE10 FPGA. So it's a full-scale operating system. So just to print the build, this is one of our builds of our servers with compartmentalisation, which we sometimes abbreviate as C18N. Yeah, it's a recent build, and it's a full-scale operating system. So this operating system can do everything you really expect it to do. So let's look at a short program. We have to demonstrate what library compartmentalisation does and how it mitigates security breaches. So we can safely ignore the print function up there. What this main function does, it calls a image compress function, and it has, so this is the external image compress function, and it has some private data, in this scenario, hello world string. I've also inserted some prints just to guide us through the program. What is the very important part is that we call a library function here, which is image compress, and then we print our data, our buffer, again at the end. So let's quickly look at the function, and we also can again ignore the print function. What image compress does is that it's actually a malicious library function, so it very much does actually not implement image compression. But yeah, that's the thing with supply chain attacks. Sometimes the library does not what you expect it to do. And so what it actually does is that it gets the stack pointer, prints the stack pointer for our convenience, so I can guide you through the attack. And then down here, after we have had some user writes here, it actually writes to P at the offset off, and the offset off is decided by us. And P is the stack pointer, so we have wild stack pointer writes. This has been both compiled or set up for the conventional case and still CHERI protection, but conventional CHERI protection and library compartmentalisation. So when we run the normal one, we see that we are in the main function. We want to compress the image. That is where our buffer is, and it's still hello world. Well, we call into the library, and then we get the stack pointer here. Now we have an offset between the two of them. I've pre-computed that one. It is 146 bytes, but I want to change the second character of this one. So I'll type in 147, and I want to change it to an A. So and now we actually made it hello world instead of hello world. We can now run the same program for in the compartmentalized case. What we see is a very much expected different stack layout. We have pretty much the same function, but when we write the necessary offset, which is pretty large offset because we need a overflow, but when we write that and we write also the A, then we see that we actually have an in-address-based security exception. So what we've just seen is that CHERI compartmentalisation has mitigated this attack because we cannot jump from one stack to the other. So we have successfully protected the stack. While this is a toy example, I think it very well shows what CHERI compartmentalisation can do. And you can easily imagine any case, any security breaching case out there in the wild. In the last few minutes, I want to take the chance and show you our software stack running. We actually have or have started porting nginx actually to CHERI RISC-V, and this actually runs with some form of library compartmentalisation. So we have started porting that, and now we need to wait maybe a second or two until nginx starts. So this is all running on CHERI Tuba, which is a superscalar out-of-order processor. So the last thing I'm going to do is actually fetch what the nginx serves us. Well, and we get something fetch out, and what this actually is the website of the CHERI website. Thank you so much for your attention. This concludes our small demonstration on library compartmentalisation. Please ask any questions. Probably I'm running out of time, so we'll need to do this after the session, but we're all around this afternoon.
Okay, thank you very much, Franz. Good insight. Nice, very brave of you to do a live demo. Thanks. Okay.